Hello and welcome to Significant Figures Calculations. In this video, we're going to do two examples of using significant figures in calculations with multiplication and division. Then we'll do two more with addition and subtraction, and then a couple where both of those things might be going on. So we'll see how to handle that. All right, so we'll start with example 1. It's 4.76 times 3.0. So in multiplication and division, we have to remind ourselves what the rules are for significant figures, and that is that our answer can't have any more significant figures, the total number of significant figures, than our least number of significant figures in our measurement. So we have to be able to count how many significant figures are in 4.76 and how many significant figures are in 3.0. So take a moment and decide that. So there's 3 significant figures in our first number and 2 significant figures in our second number. Note that I'm going to use SF, capital S, capital F, for significant figures, just so we don't have to write that out the whole time. All right, so now that we know how many significant figures are in each of our numbers involved in this math process, we need to decide which of those is the smallest number of significant figures. Hopefully this is not the hard part. So 2 is our smallest number of significant figures. So when we look at the result that our calculator gives us, this 14.28, we need to round it to 2 significant figures. So we're going to keep the 1 and the 4. And look what comes after the 4, and it's just a 2, so we'll let it all go. We'll not change the 4. And we have 14 as our answer. So example 2 is a division problem, but again, it's the same rules. We're going to look at number of significant figures and use the least number to report our answer. So we look at our first number, which is just an 8. So how many significant figures are in that? And compare that to how many significant figures are in our second number, 35.76208. And there's obviously a big discrepancy there. 1 significant figure in our first number and 7 significant figures in our second number. So which of those is the smallest number of significant figures? It's going to be the one that determines how many are in our answer, and it's 1. So our calculator gives us a nice long answer here, but we're only interested in 1 significant figure. So remember, this 0 at the front is not a significant digit. So we'll look at the 2, that's the significant digit we want to keep, and we look at what comes immediately following it, which is another 2. So as long as it's not a 5 or bigger, we will just let it all go, and we would report our answer as 0.2. So that's our multiplication and division rules. That's the one we're probably going to see most often, and that rule, again, just to repeat and remind you, is that our answer should have the same number of significant figures as whatever number involved in that calculation, whichever one of those had the smallest number of significant figures. Okay. But the rules for addition and subtraction are a little bit different. For addition and subtraction, it's not total number of significant figures, it's the position of that significant figure. Where is that last significant digit? Often people say it's the number of decimal places, but I like to refer to it as the power of 10. What position is that last significant figure in? I say that because sometimes our calculations involve things in the hundreds and thousands, very big numbers, and there really aren't any decimal places, so I don't want you to be confused about that. But most of our examples here all have decimal places here. But we'll use the power of 10. We'll see how that plays out. So here are the 3 numbers that I'm attempting to add together. And this rule almost makes a little more sense because we can't have our final sum of all these numbers. We can't know them really any better than our worst measurement. It's our one with our least number of decimal places. It's our one where the position of the last significant figure is the furthest over to the left and the biggest power of 10. So let's write down where that last significant digit is for each of these numbers. Okay. So for our first number, the last significant digit is in the hundredths place. That's the 10 to the minus 2 power, the second decimal place. in our second number, we have 1 decimal place, or the last digit being in the 10 to the minus 1 position, the tenths place. And our third number has 2 decimal places, or again in the 10 to the minus 2 power. So which of these is the largest power of 10? Which of these is the furthest over to the left, or the smallest number of decimal places? Okay, and that's our 10 to the minus 1. It's the one we know least well. It has the least number of decimal places, or the uncertainty is the furthest over to the left. So our answer has to stop at the 10 to the minus 1 position. It's going to stop at that first decimal place, even though our calculator's given us more. So we need to round it so that our last digit is right there, right after that decimal point. And if you look at what comes right after it, it's an 8. So we're going to have to round that 0 up to a 1. So our answer is 1,000.1. All right, let's try our second example. 3.233 minus 2.5709. So again, since we're subtracting in this case, we're going to be looking at position again, looking at number of decimal places, or how many powers of 10 is our last digit. So here we have, in the third decimal place, the thousandth place, the 10 to the minus 3 power for our first digit. And in the fourth decimal place, or the 10 to the minus 4th power, is where our last significant digit is. So which of those is the largest power of 10, or the least number of decimal places? That is our 10 to the minus 3. So our answer has to stop at the 10 to the minus 3 position, at the third decimal place position. So even though our calculator gave us this nice big long answer, we have to stop at the 1 to 3rd decimal place, this 2 here. So we look what comes after the 2. It's just a 1, so we'll let it go and report our answer as 0.662. Okay. And that's nice, but not every calculation in the world is just one or the other type. We often have mixed combinations, mixed mathematical things going on. We're sometimes adding and subtracting and multiplying and dividing. So let's see how we keep track of that. So we'll use as our example converting temperature. It's one of our examples from our textbook. So one thing to point out to you is that these two relationships that relate our different temperature scales, the numbers involved here are exact numbers. They are from a definition. So they have an infinite number of significant figures, and they will not limit us in our calculation. All that's going to limit us here is this measured value that we start with. So we'll see again how that plays out just a little bit here. So look at what's going on here. We're multiplying, we're subtracting, we've got two things going on. But we've also got these parentheses to remind us the order to do things in. And we're going to apply those significant figure rules in that same order, in the order that we're doing the math. So let's see how that plays out. Let's put our numbers in there. So our temperature was 102 degrees Fahrenheit. And then we're supposed to subtract 32 and multiply by 5/9. And again, keep track of our significant figures as we go. I'm going to suggest that we do this stepwise, at least at first. Don't try and do too many things at once. Is to do what's going on in the parentheses first and correctly keep track of our significant figures before we hop on into the multiplying. So when we subtract those two numbers, 102 minus 32, we get 70. And our calculator tells us 70. And what you'll note there is there's this little extra decimal place there. Well, what on earth is that doing there? Let's look at what went on here ahead of us. We did 102, which has no decimal places. It's a measured number, but it has no decimal places. And we have 32 that we're subtracting. Remember, that's an exact number. It has an infinite number of decimal places. It has as many as we need. We just don't write them all down because we don't have time for that, to write 0.000 forever. So when we subtract something with no decimal places and something with an infinite number of decimal places, our answer should have no decimal places. So all of the digits right up to the decimal point are significant, right? Unfortunately for us, it happens to be a 0. And zeros are trouble at the end there. If we don't put that decimal point, it looks like we only have one significant figure. We just have 70, 70. and that would look like that 0 was not significant. But we know it is. We know it's significant all the way up to the decimal point. There's nothing after that's significant, but right up to it, it is. So we put that little dot there to remind us that this 70 has 2 significant figures total, and the last significant figure is right before the decimal place. So that's going to come into play when we do our next step, which is multiplying. So we're going to take our measured result here, the result of a measurement minus an exact number, it's a measurement still, and multiply it by 5/9. And again, remember, the 5 and the 9 are both exact numbers, so they're not going to affect our significant figures in our calculation. Think of them as having an infinite number of significant figures. And remember, we're going to be limited by the smallest number, which infinity cannot be our smallest number. So when we multiply these out, something with infinite significant figures times something with 2 significant figures, our answer should have only 2 significant figures, regardless of where they are, whether they're in the decimal places or not. In this case, they happens to come out to be 39. All right, so let's apply that again in this case down here. Let's change our temperature of 39 degrees Celsius into the Kelvin scale, which is a temperature scale that we'll see quite a bit more in Chapter 5, but we get to play with it now in Chapter 1, just as we're practicing. And it is the degrees Celsius plus this exact number. Again, even though it has decimal points in it, it's an exact number. This is a definition of what the conversion between these two scales is. So this really should be 273.15000000 all the way on to infinity. But again, we don't write that. We just have to know where this number comes from and how it is related to significant figures. Okay, so let's take our 39 degrees Celsius and pop it into our equation here and take a look at what's going on. In this case, we're just adding. There's going to be no multiplying. So we have to remember our rules is to look at the number of decimal places, or the position of where the last significant digit is. So for our 39, the last significant digit is this 9 here. It's in the no decimal place position. Over here in our 273.15, there is no last significant digit. Remember, this has an infinite number of significant digits. It would have really a whole bunch of zeros written all the way after it. So it's not going to limit us in any way. It clearly isn't going to have the biggest power of 10 where that last significant digit is. So this number, our 39, is going to limit us. So when we add these two numbers together, whatever our calculator says, we need to round it so we have 0 decimal places, just like our limiting number here. So 312 Kelvin, 312 K is how we would write that. Well, thank you for joining me for Significant Figures Calculations. I hope you found it helpful. We'll see you soon.